Hello, I'm Tom Lucas with Purdue University. I teach advanced manufacturing in our Greater Louisville area campus right across the river from downtown Louisville. And today I'm going to be talking to you about nanotechnology. We'll look at the definition of nanotechnology and zoom into what it actually means at an applied level in the modern day. We'll talk about the life cycle and requirements to create nanotechnology infused applications, and then we'll look at the impact across various areas of our world. So in general, when we talk about nanotechnology, we're talking about creating elements that are very small, much smaller than we can visualize. So if we look at our scale here, on the very right hand side we have a watermelon moving left through a few common items. You have a dime and then a hair at 100 micrometers. We're still too large. A red blood cell, which most of us have encountered in our education at some point. The concept of a red blood cell is still a number of micrometers, which is thousands of nanometers. So going smaller still, nanomaterials and nanotechnology, those elements are in a space between the size of molecules, but still much smaller than most cells in the human body. And so when we talk about nanotechnology, we're really talking about materials that can create, materials that can be created that have elements to them or design to them at the scale of, between a molecule level and still smaller than a cellular level. And this is not a brand new concept. Nanotechnology is well established in a lot of sci-fi and fiction. Some of you may be familiar with the application up on the screen here of the Borg in the Star Trek series. But in reality, we're not quite to the point where we are actively applying nanotechnology in all facets of life, although the research area is huge. There are applications envisioned and being worked on at very smaller scales in various areas of engineering and defense and medicine, consumer products such as fabrics and cosmetics. And the applications there are being developed because nanomaterials have a lot of unique properties that we can utilize. When you move down to the scale that we saw on the previous slide, nanomaterials give you extremely smaller than a wavelength of light elements, and because of that, they start to exhibit unexpected properties because their size relative to their amount of surface area begins to change dramatically, and that affects a lot of properties, from the way they absorb light to the way they transfer heat and energy into and through and out of nanomaterials. Because their volume is so small and their surface area is so big, the behaviors are much different than we encounter in our sort of day-to-day human scale. But as we begin to learn more about and harness these different properties, applications are being developed in universities around the world and companies around the world in many different fields. And what we're going to talk about today is really what advances for society could new nanotechnology products enable, how might nanotechnology benefit humanity in various sectors of society. And along with new technologies, there are also new risks. So how can we prepare for unexpected risks? And kind of the answer or thing to consider around all of these is what changes occur as you move down to a nanoscale. So we're going to look at more details of framing nanotechnology and what scale means in the context of this discipline. And we'll look at the life cycle of a nanotechnology infused product, which is going to touch on new and different types of material requirements and manufacturing techniques and disposal methods. Because of the non-traditional nature of nanomaterials, because of their properties that differ from larger scale things, a lot of our existing infrastructure has to be adjusted to accommodate new types of materials using nanotechnology. And then finally, we're going to connect those elements of the life cycle up with impacts on humanity and different economic sectors. So a lot of sections 2 and 3 in particular are going to focus in on example applications and some just exercises expanding on how nanotechnology is going to impact those areas. So let's start off with just generally defining nanotechnology and the idea of nanoscale. Scaling is how we make nanotechnology useful in an actual application for humans. And we're not talking about magnification style scaling, like make something twice as large, but nanotechnology scales by multiplying. Because when we're interacting with one cell, that is the level at the design of nanotechnology that we're at, but to actually apply that to a human body, which has tons and tons of cells, you need to have massive multiplication of your manufacturing capability and of your nanotechnology infused material in order to make it useful at scales that we interact with. So we'll look at sort of some issues of scale, advantages, and changes that occur when you scale materials large and small, kind of see how these connect up to relevant examples at the scale that we interact with as people, as well as some of the challenges. So as I already mentioned, the design of a nanoscale device is usually envisioned conceptually as one element interacting with one virus or bacteria or cell. And the ability to engineer materials at this scale can give some really unique and new opportunities. But we need to kind of consider what nanotechnology actually looks like. So a lot of our kind of engagement with nanotechnology is in the realm of fiction, and so we imagine nanorobots. But that's not really what we're talking about in this case. Kind of the visual that's shown here, near impossible to manufacture. The concept of that appears in a lot of our common societal kind of discussion of nanotechnology is based on the idea of kind of like the machine shop atmosphere where you're making something with traditional tools that we understand. But the actual creation of nanotechnology uses tools that we're not so familiar with visually, that we don't interact with our hands. The tools are chemistry and replicating biological processes that we possibly couldn't even replicate ourselves with our own tools, but since we're able to harness some of these biological elements, we can create nanoscale materials. And so actual nanotechnology and the tech that is infused into other products tends to be created in bulk or in large batches and performs a single function. So this would be things like having a crystal growth in a particular way, having very thin films and sheets being created of a material. Again, not one nanoscale particle, but entire sheets or films of this, or having chemicals that you mix together and you'll have nanoparticles or nanotubes precipitate out of that material in bulk, and you can collect them in bulk. So a lot of when you do an analysis of a piece of nanotechnology, what you're analyzing is a bulk sample. So you're talking about very large numbers and looking at averages and statistics of what you're looking at. There are technologies that allow us to zoom in and look at individual elements at that scale, but those individual elements are really of the greatest interest at the research end of applications. And as we try to produce materials to be used for a particular application, we have to look at big batch samples. But even with those restrictions in place, materials have different properties just due to different size benefits. So at that scale, the volume is very, very small compared to the amount of surface area. You have sheets of material that are so extremely small that their surface area is overwhelming, and this can have additional effects on the electrical and mechanical properties of a particular surface. And at this scale, even when we're talking about large batches and production of materials, we can look at precise control of a sample of nano particles, for example, interacting with a sample of blood and red blood cells. There are hundreds and thousands of particles and cells interacting together, but viewing the average behavior, an individual particle and cell interaction has been designed at some level, but then the behavior that we observe tends to be large averages. And I'll expand on that a little more. So nanoscale does not mean one nano-sized application. You need large scaling of a nano element to be applied to something that's actually going to impact us and be meaningful at the human scale. So for example, in a few areas, nanotechnology can be involved and scaled to a point that it's useful. In medicine, for example, particles can be designed with chemical coatings or surface functionalization that allows them to attach to certain types of cells or viruses or bacteria. Those particles aren't complex in their very nature. They tend to have one or two very specific functions. Perhaps they bind to a certain type of cell, maybe a cell that has been indicated to be cancerous, and a certain functionalization is done so that the particles attach to just that kind of cell, and then maybe those particles, when exposed to certain types of light or a certain energy, just heat up and destroy the cell they're attached to. Destroying one cancerous cell is at the core research level what you're going for, but you obviously, if you have a larger cancerous mass, there are many, many, many cells and many, many interactions of nanoparticles required. So the application of nanotechnology is typically not at the nanoscale. It's the application at human scale of some element that had a nano component. Electronics are similar. In every cell phone in existence, produced in the last decades, there are elements of nanoscale design involved. When you talk about nanoscale transistors and you're fitting trillions across a chip that's as wide across as your thumbnail, the nanotechnology element of a single chip did appear and is appearing in continuous design and improvement, but it's actually the scale, making hundreds and thousands and hundreds of thousands of nanoscale individual elements together to make a single processor to go in a cell phone, for example. That's what actually functionalizes that nanotechnology. So it's important to consider when we think about applications that we're really wrapping our head around applications that involve small elements interacting with small elements, and then what does a bulk batch mass of that look like? In the realms of energy, nanotechnology is, and you can find many sources for nanotechnology integrated with energy, but it is not that we're making nano-sized batteries, it's that we're able to make special coatings or films that enhance efficiencies of solar cells or increase the ability of batteries to charge and discharge at higher rates. So when we're improving different types of energy storage and movement and production with nanotechnology, it's with or in combination to other macro scale technologies as well. And we're utilizing some of those special features and scaling them up. Final example in this batch here is related to environmental remediation, so something like air filtering or water filtering. Nanomaterials can interact with particles in different ways than maybe a traditional filter would. We've obviously seen in the news new challenges with things like microplastics appearing in all types of places around the world, above and below soil, things like that. And in unexpected places, there may be opportunities to make targeted particles and create coatings out of those particles that can interact or attach themselves to unwanted waste in some way. And so, approaching problems that scale is really where nanotechnology has a lot of power and ability. But with this scale, still it does introduce new challenges. The idea of safety and potential health risks is obviously very present. A lot of our safety standards are based on physical things that we interact with at our human scale. And so as we move to using a lot more chemistry and biological elements, it does include the question, or bring up the question, does our kind of standardized safety still work when you move at this scale? Something like an air filter that we all have in our air conditioner at our home, if you really zoom in, and you can see all these interlocking wires here, but the scale bar lets us know that's still 20 micrometers or 20,000 nanometers. So at the scale of a nanoparticle, if we are aerating a dusting of microparticles that do something, they can float right through a filter like that. And so without any prior consideration, we can be unknowingly maybe contributing to a problem that we didn't really think out if we only use pre-existing technologies or current established technologies, because nanoscale elements introduce new factors when you have just these large batches of very specifically targeted small particles or tubes, or not a single atomic level, but smaller than cellular level, certainly, elements. But despite these challenges, nanotechnology does have potential to revolutionize various industries, give us a lot more and newer functionality. The reason is, when we solve a problem at nanoscale, and just sort of the nature of now repeat that a million times to get a batch big enough to create a new solar cell or coat a car so that the paint lasts longer and is more robust under various conditions. Whatever your application may be, the element of scaling it actually folds quite nicely into the way we manufacture things in the modern world. So the idea of mass production is in place here. It's just the tools lean more chemical and biological, typically for nanotechnology, as opposed to traditional electrical and mechanical, primarily, modes of manufacturing. And I do want to explore those modes of manufacturing a bit more, because there are going to be new challenges at each stage of nanotechnology's life cycle, from sourcing different types of materials and creating different reagents and waste quantities as you make materials. When using nanotechnology, we're introducing new concerns with storage and movement, and even types of containment. And then on the disposal end, there are environmental issues to consider, and just overall waste issues to consider, looking at the cost of these processes, which might require new types of technologies at each stage. So there is tons of basic research in nanotechnology going on all around the world, and proof of concepts tends to be small, like think a desktop, like a beaker scale proof of concept. The scaling is a lot of the barrier towards a lot of our nanotechnology implementation. And that's not to say there's not tons of unexplored applications. There are absolutely a huge range of unexplored applications that I'm sure we will come into in the coming years and decades and centuries, probably. But for things we have figured out at the research and proof of concept level, scale is a lot of our challenge. And so the advanced manufacturing of these type of elements and integrating them into things we can use and distribute and dispose of in our societal structure right now is a lot of where we're at. So what I'd like to do in this section of the talk is just go through parts of the life cycle, highlight some issues related to nanotechnology. This kind of gives us a framework for working with what will the implementation of more nanoscale advancements, what will including that in our current processes do, and how will that kind of impact the normal working order of things as it stands in the industrial area. So nanotechnology, we've already kind of mentioned what it is, but developing nano-related materials might involve new types of material extraction, nanomaterial synthesis, and movement. And then there are manufacturing challenges with integrating, kind of batch nano-produced items into day-to-day operation. So integration with real products, whether it's application in a medical device or on a manufacturing line for a consumer product. And then once these things make it through the industrial manufacturing space and are on the shelf at your local retailer, what does consumer use and disposal look like for these type of materials if they're over the counter, if they're medically related, or just you can buy them at the store and discard them? And so that also ties in some end-of-life concerns around recycling and recovery. And assessment of these items is ongoing. So let's just start at the beginning. Raw materials for nanotechnology tend to require a few precise qualities to them. You need purity and consistency because of the scale that you're working at. Although you're creating in batches, any impurities are highlighted and multiplied as you scale up your batch process. And so availability becomes a concern as a lot of research and development activity works at much smaller scales. And so if you want to make a mega factory for creating mass quantities of a nano-infused substance, availability concerns are there. And acquiring materials to bring into this process introduces new health and safety concerns. So as already mentioned, the purity and consistency is a major factor. It's not like a beam of steel, and if there's some dust on that steel, it's all going to kind of come out in the wash. When you're working with chemical processes, whatever comes in is sort of averaged across the quantity and makes its way out as well. So it's said in a lot of the silicon industry producing chips that one fingerprint can spread to about 6 square inches on a chip. So if I went to Intel and touched a silicon wafer where they were making processors with my bare hand, the whole chip would immediately be ruined. And you've maybe seen imagery of clean room applications where everybody wears a full body suit and ventilator and stuff. That's to prevent impacts on the purity from even particles that our bodies produce. So nanotechnology puts us in a space where our bodies are not meant to exist. We have a lot of elements that can impact purity and consistency. So availability speaks to the ability to acquire chemical materials that may be accessible at a small scale at a research laboratory, but scaling them up to make a consumer product that you're delivering across the country may or may not be possible depending on the rarity of a certain material. And this is kind of a per application concern. And when producing new materials, there can be unintended consequences, just like the air filter that doesn't necessarily stop nano elements. In the past, we're not bombarded or surrounded unintentionally by a lot of nano elements, as we would be if we were producing something that was aerosolized, for example, or passed in the air. If we're introducing particles that interact in some unknown way, kind of the health concerns and environmental release begins to come to the forefront. But with planning and collaboration, definitely investment in research can start to figure out what are these issues and how we can deal with them. So once you've developed your techniques and found availability of your materials and a way to handle them, the manufacturing and distribution brings some new elements. In particular, around the cost and validation of products, and then supply chain issues, as you may need new ways of transport, as well as intellectual issues because of the high research cost of examining things at nanoscale. Your intellectual property could be limited, so there's pressure if you're trying to distribute broadly versus having a very limited pipeline of suppliers who know how to make your product. The production costs go up because a lot of those purity consistency concerns are in place. You may have environmental, very strict environments where you need to do your manufacturing, so regulating temperature and humidity and surface cleanliness and things like that. Validation of nanomaterials, again, requires a lot of specialized equipment. A standard microscope is not going to be looking at nanomaterials. You need a scanning electron microscope. Highly trained staff. Characterization of these does involve sort of more intense lab testing in more clean environments, things like that. So overall, working in this area is a very high cost endeavor. Even once you make batch nanomaterials, there could be supply chain issues if you're requiring constant refrigeration or have safety issues around the packaging. And IP issues kind of roll into the supply chain issues in that because of the high cost, you'd probably have limited chains or pathways where this material can get to where it needs to go to create your end goal product. And so protecting IP while kind of dealing with supply chain concerns around geopolitical events and natural disasters can result in very limited quantities, which can again boost cost and lead to some other issues related to consumer access and ethical issues just in the use of the products in general. So after manufacturing and distribution, you have the use. Once the product gets to the consumer, there are health issues as well as information. How do you inform a user about a product that they have no conceptual knowledge of how it works? And so kind of crafting the language to be informative and useful and authentically honest, I think will be a big area where nanotechnology needs to be developed, just in terms of the marketing and communication, because it's conceptually approachable because of our engagement with fiction through the years, but the reality of nanotechnology is quite different, and the minute details of how nanotechnology infused elements can react with other things needs to be communicated in some way that's understandable, but to the general populace. And at the end of life, you have additional, because you have new materials, you have uncertainty in how they're going to be dealt with, and you can't just keep making more and more and more nanotechnology infused elements, throwing them in the garbage dump, and then you find out they're kind of going into the rest of the garbage and creating something toxic or destroying the earth or the atmosphere or things like that. We could have unintended consequences, or they get evaporated and spread by the rain across the land into other areas and our food sources and things like that. So knowing where the products go at the end of their life is also key. But during use, toxicity and long-term effects are obviously medically relevant concerns that we see in a lot of current products. Is just the reason for those issues tends to be different in nanotechnology infused elements. The consumer will be very susceptible to misleading claims and marketing just because of how different nanotechnology is from common sense developed living in a macro scale world. And that will lead to ethical issues making sure that there is both access and appropriate information being delivered about nanotechnology infused products if they become at a scale where they're widely available. And then the products themselves, kind of detached from the humans, involves what do you do with it when we're done with the nanotechnology element. You need to avoid destruction of wildlife or harm or the climate, things like that. Again, just like you scale nanotechnology from one cell up to a large batch, if you have 500,000 nanotechnology product users all discarding continuously, we now have scaling to the scale that we're affecting our land and the planet and things like that. So this could, if not properly regulated, sounds like sometimes a harsh term, but just kind of monitored and dealt with in a clear way, there is some regulation required in how these products are released, because they are unnatural and existing ecosystems are not built to deal with technology engineered at the nanoscale. But research and development really needs to be very highly funded to figure out what a lot of these issues are and try to prevent as many as we can as we move through increasing output in nanotechnology related fields. And with strategies and for sustainable and responsible use and disposal and equitable distribution, things like that, it is possible that we can enhance parts of society with nanotechnology. So that kind of approached what is the impact on humanity, which was our third big question that we wanted to discuss. But much of what we saw in the life cycle was simply what is required to make these products exist. And so what I wanted to look at in this third area is, when utilizing nanotechnology, what areas of society will that start to impact? And the applications are numerous in a very wide range of things across medicine and energy, education and research, public health, transport, all kinds of stuff. So separating that into a coherent list is one of the challenges, because nanotechnology is such a broad topic that doesn't just have one clear target application. And so what we're looking to do in this last section is just give a framework for, given a potential application, of which there are many that can be discovered on your own using just online resources and things. But given a particular application, how does that plug into kind of quantifiable aspects of humanity or our society? And so the approach I'm going to present is breaking down the impact to humanity as kind of looking at different global industries and sectors. There are a number of lists, or what are the sectors of the economy. I found one that generally tried to capture everything. And I wanted to look at, given the new requirements of the nanotechnology development and life cycle, how do those benefits and risks plug into these different industries and sectors? And by doing that, I'm looking to map the impact in different areas. And so a lot of the benefits of applications were involved in medicine and material science, electronics, energy, environmental remediation. We'll talk about those in just more detail in a moment. So zooming in a little bit, in medicine, you can have more effective drugs, drug delivery, targeting of specific diseases or viruses, interaction with cells at an individual cellular scale. If you're trying to maybe repair a problem or enhance a property of a particular cell's work that it does. But that does have some fallout in a few different sectors. For pretty much every benefit and risk, education and research is touched, but I don't highlight it for every single one. You'll see it pop up in particular for a few. But for medicine, I highlighted private sector services and public utilities and health. Obviously, this involves our healthcare infrastructure in general, is going to be pressed to manage very targeted, high cost, at least initially, nanotechnology developments, and sort of manage the distribution of those and determine who gets what and how, and what are the use cases that are worth employing high-cost nanotechnology. So there will definitely be some exercise and management in the healthcare sector. But also under the idea of medicine is the idea of cosmetics. Nanotechnology will be the 22nd century snake oil salesman, if you will. Just put nano in the name, and you may have an all-new healthcare therapy kind of thing. And so there's going to be a lot of private sector interaction, both in honest and dishonest ways, that will require some consideration on how we deploy nanotechnology to consumers for use on their own bodies and their own cells. In the material science area, we are creating materials with new novel properties based on that scaling, the ratio of volume to surface area effects. A lot of the electrical and mechanical capabilities of materials. And so producing new materials does involve new sources of energy and mining. If we're not making things out of steel anymore, we're making things out of more rare chemicals. That has some big implications on where do we get those chemicals. In the manufacturing space, there will be issues of scale and working with new materials, using very new and specialized processes. And then we're going to have to develop infrastructure to make use of nanotechnology if we're producing a lot of it. And so there will be interaction of, as it relates to material science, new forms of building materials that have higher strength and less weight, or more resistant to earthquakes or high heat damage, things like that. And so our infrastructure will see integration of nanomaterials, not that our power lines will suddenly be replaced by tubes of nanoparticles, but that we'll have coatings and mixes and new types of concrete that have a nano-related element in them, but it's scaled up to a form that we use with our everyday life. In the electronics realm, nanotechnology is probably at the forefront because electronics really drilled down to a small scale very quickly in the previous decades. But again, you'll see smaller, faster, smarter, and I'm using smarter in sort of the computational way. Electronics, currently we're seeing a large growth in the amount of processing power needed for electronic and software applications related to all the large language models and AI in development and becoming very popular in the public space. And running all those utilities as people go to a prompt to ask a healthcare question rather than a doctor, but that all has to be run through large energy data centers, and making smaller things, making faster electronics can help mitigate some of the energy uses required in those spaces. In the private sector, you're going to see new advancements and new types of computing, also related to getting new efficiencies in what we can calculate and the kind of supercomputing we can perform in the private sector if we have new and enhanced materials that exceed efficiencies of what we're using right now. In the energy realm, improving battery storage and charging becomes more critical as we have a more battery reliant world. Obviously, we have smaller scale batteries in our phones and cameras and everything. Electric vehicles aren't seeing the explosive growth they were in the previous couple of years, but still a stable force and constantly under development. And so finding ways to improve charging time and efficiency of discharge, all critical areas where new materials can help out approach some of those challenges. And that's why I highlighted maritime and transport as well, as we look for electric modes of transportation interacting with energy in new ways becomes critical. And new materials based on nanotechnologies can help us interact in new ways. We also deal with the consequences of our society and our production already. And I highlighted earlier the issue of microplastics has become kind of pretty well known lately, as that they're showing up in pretty much everywhere. But there may be solutions to create nanoscale materials to help, clean up elements of the environment. So this could be, while we can't use a shovel and scoop microplastics out of the dirt, if we can make one particle that binds to one particle, then scale it 1 trillion times, we now can run a liquid through a chunk of dirt and maybe clean out some element of that, hopefully without introducing new concerns. So there's the agriculture, food, forestry industry related to growing and usage of chemicals may find some use of nanotechnology elements. But high levels of education and research are required here. Both education, because you need specialized training to make a lot of these new products that may come out in the future, and then research to kind of consider the issues. Well, if we make a particle that attaches to a certain contaminant, are we going to be introducing other issues? And so research kind of covers that scope as well. And within agriculture, we have increasing evidence of impact from pesticides and usage of unnatural techniques to improve crop yields, and there may be ways to find increased kind of sustainable practices in agriculture and food fields that have non-harmful effects to our food and health and things like that. So nanotechnology may find a space when you're applying something in bulk to a whole field of crops. Could you make a solution involving a nanotechnology related element that is useful for that? Possibly. But the flip side of a lot of these advancements there are new considerations to have around a few areas. There are health risks. The other side of integrating nanotechnology with our agriculture is that we're now ingesting or releasing into the environment some of these issues, and so or some of these materials, and so there will be private sector and food and forestry attempts to kind of quantify this and hopefully mitigate damages. And a lot of that's related to the environmental impact. If we're deploying solar cells or new types of concrete with integrated nano elements in our infrastructure or in our healthcare, in our medicine, what does the disposal or even just usage of these elements day to day do when you have a building made of nano-infused concrete sitting in the middle of a city? Maybe you now have 100 buildings with this concrete. Is some of that coming off into the rainwater and moving somewhere it wasn't intended? And so there will be a lot of pathways to follow up on as we try to investigate the impact of nanotechnology. As you require more specialized technicians to make the technology, more specialized manufacturing to produce it, you're raising cost. And so the idea of who gets access to this, is it only folks that are of a certain level of means, or is it based on need, based on condition? There are ethical concerns in the healthcare space, as there frequently are. And there are also concerns around the mining and acquiring of new types of nanomaterials as well that may not be as readily available and may require new harvesting techniques that are dangerous or unregulated in some other way. And so research into these areas on how we can regulate and sustainably integrate nanotechnology into our current society and economy requires additional research, and then education is required to create a workforce that can actually produce and keep up with new types of technologies, which will require new manufacturing techniques. And the goal of a lot of the considering ethical concerns and considering regulatory challenges is to try to avoid creating disparity or distributing in some unequitable way that's going to exacerbate problems in our society. And so a lot to think about there. I don't have the end answers because nanotechnology is so broad and new, and there are countless applications being envisioned. But it's the scale of these products that gives them different properties. And then once a property is designed, scaling that process back up to a size that we can use offers potential benefits in medicine, material science, electronics, energy, and many others. It can, lead to new or effective treatments that are highly targeted, enhance our ability to use electronics and do more efficient and useful number crunching with computer devices, improve energy storage and manipulation, which can help ease our concerns for energy a bit as it relates to harvesting from the environment. So what I wanted to provide here was largely an infrastructure to allow you to talk with your students about new applications, and as they maybe are interested in a particular area and dig into it more, find some applications, you'll have a way of mapping those to different elements of how they affect us. And also for thinking about the potential risks, concerns, but the benefits are promising. And luckily, our students are already primed to consider this nanoscale applications across all realms of the economy. But this framework, looking at the different sectors, will help keep them focused, help be very specific about what those applications mean, which will make the discussion more useful and more impactful as your students produce solutions of their own. So, thank you.